In this section, 11.5, we're going to look at operations in probability and the statements or, and. So what you will learn in this chapter is how to calculate compound probability, know how to calculate probability for or problems, know how to calculate probability for and problems, and for the and problems, there is two types of probability to be calculated. One under independence and one under dependence. So our objective ultimately in this section is to learn how to solve compound probabilities problems that contain the words and or without constructing in a complete sample space. The or probability problems require obtaining a successful outcome for at least one of the given events. When we say or, it is a union typically of two events. You will recall from set notation that the probability, or actually the number of A or B, equals the number in set A plus the number in set B minus the number in set A and B. In probability, we do the same thing. To determine the probability of A or B, we use the following formula. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So in this statement, the probability of A plus the probability of B is the events A and B and their probabilities associated, and then we subtract off the overlapping probabilities of A and B. This is called the addition property of probability. So suppose we have the following. Each of the numbers 1 through 10 is written on a separate piece of paper. The 10 pieces of paper are then placed in a hat, and one of the pieces is randomly selected. We want to determine the probability that a piece of paper selected contains an even number or a number greater than 6. So in this, we're going to go back to our idea of Venn diagrams. We're drawing a Venn diagram, and we're looking at the set A, which contains all of the even numbers, and set B, which is the numbers greater than 6. Now, we're going to find out what is the probability of even. Well, there are 5 numbers in set A out of a possibility of 10. So the probability of even is 5 divided by 10. The probability of a number being greater than 6 in the hat is, well, there's 4 numbers in B, so it's 4 divided by 10. Notice that we have the situation where we have 2 even numbers that are greater than 6. That's an overlap, and therefore the probability of both even and greater than 6 is going to be 2 over 10. Now we're going to plug in the actual numbers to find the probability of the event even or 6, which equals the probability of even, which is 5 over 10. The probability of a number being greater than 6 is 4 divided by 10. And now we're going to subtract out the overlap, which is both, which is 2 over 10. We end up with the probability of 7 out of 10. So, for this probability, the 7 numbers that are even or greater than 6 are 2, 4, 6, 7, 8, and 9. So the probability of a number being even or greater than 6 is equal to 0.7 or 7/10. So two events that are mutually exclusive if it is impossible for both events to occur simultaneously. If two events are mutually exclusive, then the events A and B, the intersection, is equal to 0. The addition formula simplifies to just the probability of A or B is equal to the probability of A plus the probability of B. In this case, if we went back to the Venn diagram, we would see no actual overlap between event A and event B. So here's our example. One card is selected from a standard deck of playing cards. Determine whether the following pairs of events are mutually exclusive and determine the probability of A or B. So we want to determine that A is equal to an ace and B is equal to a 9. If in fact we're drawing one card out of the deck, it's impossible to get an ace and a 9 at the same time. So therefore, we have the mutually exclusive events. We have the probability of getting an ace or a 9 for one card is equal to an ace plus the probability of equal to a 9. That is 4 over 52 plus 4 over 52. If we add that, we get 8 over 52, which is 2 over 13. Now suppose we select a card, and the card can be either an ace or a heart. Now, there is a possible intersection because the ace could be the ace of hearts. So we don't have mutually exclusive events. And in fact, in this case, the probability of an ace or a heart is equal to the probability of an ace, which is 4 over 52, plus the probability of a heart, which is 13 divided by 52, minus the probability of the intersection of being a heart and an ace, which is 1 over 52. And when we do the math, we get 16 over 52, which is 4 over 13. Now we want to calculate if the card is either a red card or a black card. Well, again, in this case, the events are mutually exclusive because if we select one card out of the deck, it cannot be a red card and a black card. So it's impossible to select both. Therefore, we have the following. The probability of a red or black is equal to the probability of red plus the probability of black. When we do the math, we end up with 100%, 1. In one of our last examples, we again select a card from the deck, and now we ask the question, is the card a picture card or a face card, or is it a red card? And in this case, it's possible to select a red picture card so we don't have mutual exclusive events. Therefore, the probability of a picture card or a red card is equal to the probability of a picture card plus the probability of a red card minus both. So in this case, we have 12 over 52, which is the probability of a picture card, plus the probability of a red card is 26 over 52, minus the probability of it being a face card and a red card, which is 6 over 52. When we do the math, we get 32 over 52, or 8 over 13. Again, we can express this in decimal form. So for AND problems, requires obtaining a favorable outcome in each of the given events. In other words, it is the intersection of both events or the overlapping of both events. So to determine the probability of A and B, we use the following formulas. If our events are independent, in other words, the probability of A does not affect the probability of B, then we just have the probabilities of A times the probability of B. However, if our probabilities are dependent, in other words, when we do the probability, if we do the event A, and it affects or changes the probability of B when we do the experiment B, then the probability of A times the probability of B given A has changed, and therefore we call it a dependent event. Both formulas is the multiplication property of probability. Since we multiply to find probability of A and B, this formula is referred to as the multiplication formulas. When using multiplication formulas, we'll always assume that event A has occurred when calculating event B, because we are determining the probability of obtaining a favorable outcome in both of the given events. So here we have an experiment without replacement. Two cards are to be selected without replacement from a deck of cards. Determine the probability that the two spades will be selected. The solution is the probability of selecting a spade on the first draw is 13 divided by 52. Assuming we selected a spade on the first draw, then the probability of selecting a spade on the second draw has changed to 12 divided by 51. That's what's left in the deck of cards. Now we want the probability of two spades. Well, that's equal to the probability of the first spade being selected times the probability of the second spade being selected, given that the first spade was a spade. That is 13 divided by 52 times 12 divided by 51. This equals 1/4 times 4 over 17, which in this case equals 1 over 17. So in recap, event A and event B are independent events if the occurrence of either event in no way affects the probability of the occurrence of the other event. For example, rolling dice and tossing coins are examples of independent events. They don't change the probabilities on the next experimental try. So in the next situation, we ask whether or not the events are independent or dependent events. 100 people attended a charity benefit to raise money for cancer research. 3 people in attendance will be selected at random without replacement, and each will be awarded the door prize. Are the events of selecting the 3 people who will be awarded the door prize independent or dependent events? Well, the key here is without replacement. If we select people without replacement when we're doing the drawing, of course, guess what? It's going to be dependent events. So therefore, the solution are dependent, since each time one person is selected, it changes the probability of the next person being selected. So the probability of person A is selected is 1 over 100. The probability of person B is actually selected, then of the second drawing, then the person A is selected is 1 over 99. In general, any experiment in which 2 or more items are selected without replacement, the events will be dependent. So in this section, we learned how to calculate the following probabilities. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. the probability of A and B, if it's independent, is just the probability of A times the probability of B. If they're conditional, that means if they're dependent on one another, then the probability of A times the probability of B is really, or A and B, is equal to the probability of A times the probability of B, given that A has changed or has occurred first. So that concludes chapter 11.5. We will be covering conditional probability in 11.6.